Hello, my name is Dennis Morris. I'm a mathematician and a theoretical physicist. I specialise in the study of empty space. In these videos I am showing you my research into the nature of empty space. This series of videos will culminate in the derivation of our four-dimensional space-time as a unique superposition space. In the video previous to this video, we saw two-dimensional space-time emerge from the finite group C2, and we saw the two-dimensional Euclidean space emerge from the finite group C4. What kind of spaces emerge from the finite group C3? This will blow your brains out. We are about to meet four three-dimensional spaces which are nothing like anything you have ever seen before. How do we do it? We proceed in exactly the same way with the group C3 as we proceeded in the previous video with the finite group C2. We begin with the permutation matrices which form the finite group C3. We multiply each permutation matrix by a real variable, and we add these matrices to form the algebraic matrix form of the order 3 cyclic finite group C3. That was easy. We then take the exponential of the algebraic matrix form, and we get the polar form of the space. Note that since the real part of the algebraic matrix form, the leading diagonal, commutes with every other matrix, we can extract it and take its exponential separately. We use the Greek letter nu to denote the functions in the angular matrix of the polar form. The matrix with the nu functions is a rotation matrix, and the nu functions within this rotation matrix are the trigonometric functions of this three-dimensional space. Note that the nu functions have two variables as their argument. This means that the three-dimensional angle is a two-variable angle. Since the determinant of the exponential of a matrix with zero trace is always unity, the determinant of the rotation matrix is unity, as it should be. What? An angle formed of two variables? You've not seen that before. I've seen that before, but you might not have done. When we looked at the two-dimensional spaces, we saw an angle formed of one variable. That one variable was the one non-real part of the algebraic matrix form. The two-dimensional spaces have one real part, the identity permutation, and one imaginary part. The rotation matrix comes from the imaginary part, and so you have one variable for your two-dimensional angle. In the group C3, we have two imaginary variables, two permutations which are not the identity permutation. The rotation matrix is the combination of both those imaginary permutations. And so a three-dimensional angle has two variables. The four-dimensional spaces come out of the order 4 groups. Order 4 groups have three imaginary permutations. That's three permutations which are not the identity. Thus, a four-dimensional angle has three variables. A five-dimensional angle from the finite group C5 has four variables in the angle. And so it goes on. It's only fair if you think about it. A two-dimensional angle has one variable, a three-dimensional angle has two variables. It's only fair. Unless you are familiar with my research, you will never before have seen a three-dimensional angle, or indeed three-dimensional rotation, or four-dimensional rotation. Within our four-dimensional space-time, we are familiar with only two-dimensional rotation. We are familiar with two types of two-dimensional rotation: rotation in space-time and rotation in the Euclidean space. In our four-dimensional time, we have two types of rotation. That's two types of angle. That's seemingly insane. One type of space with one distance function should have one type of rotation, should have one type of angle. We have two. Furthermore, our four-dimensional space-time ought to have a four-dimensional rotation. We have two-dimensional rotations. Our four-dimensional space-time is not at all natural. To reiterate, the most startling thing about our four-dimensional space-time is that it has two-dimensional rotations, and two types of them. Most unnatural. Compared to that, a three-dimensional space with a single type of three-dimensional rotation and a single three-dimensional angle is entirely sensible. Well, I suppose you are hanging on the edge of your seat, wanting to see these three-dimensional trigonometric functions. Of course you are. Everyone is. These are the three-dimensional trigonometric functions of this three-dimensional C3 space. Look at the signs carefully. Are these really trigonometric functions? Let me confess. When I first discovered these functions in 2005, I could not bring myself to accept that these were trigonometric functions. Indeed, it was 3 months before I started to see that these were trigonometric functions, and it was 18 months before I became completely convinced that these were trigonometric functions. Thus, I know I need to convince you that these are trigonometric functions. Let me show you a few things about the new functions. A rotation through an angle, say theta, combined with a rotation in the opposite direction through the minus theta, brings us back to where we started, which is the identity. The same is true with a space-time angle. An acceleration followed by an equal deceleration brings you back to the velocity at which you started. We see that the new functions have exactly this property. As series, the two-dimensional trigonometric functions are based upon two-way splittings of the exponential series. The hyperbolic trigonometric functions are direct splittings of the exponential series. The Euclidean trigonometric functions are identical to the hyperbolic trigonometric series, except for the alternating minus signs. We see that if we are to set either one of the two variables in the new functions to 0, we get three-way splittings of the exponential series. This matches the two-way splittings of the exponential series, which are the two-dimensional hyperbolic trigonometric functions. The new function rotation matrix with the two non-zero variables is just the matrix product of the two new function rotation matrices with a zero variable. Of course it is. All we have here is the product of two rotation matrices being another rotation matrix. There is much that is profound about the previous statement. If you have not seen this before, you should be sitting there with your mouth agape in surprise. These are remarkable functions. This is a very different kind of rotation from the familiar two-dimensional rotations. The series for the two variable new functions is also related to the exponential series. What about the differentiation cycle? If we differentiate a cosine, we get the sine function. If we differentiate the sine, we get back to the cosine function. We have a cycle. Similarly, the sine and the cosine cycle in differentiation. Do the new functions have a differentiation cycle? Of course they do. We see that the differentiation cycle is a little more complicated because we have two variables. If your doctor tells you to go cycling for exercise, just differentiate trigonometric functions. It's as easy as falling off a bike. We have the double differentials are equal to themselves. Well, are you convinced that the new functions are genuine trigonometric functions? No, you're not. If you were strictly logical, you would be. But your heart is full of preconceptions and prejudices. As I said earlier, it took me 18 months to accept that these were trigonometric functions. What is a trigonometric function? A two-dimensional trigonometric function is a projection from the unit circle onto one of the two axes of the space. The cosine of a two-dimensional Euclidean angle is the projection from the Euclidean circle onto the horizontal axis of the Euclidean plane, and the sine of a two-dimensional Euclidean angle is the projection from the unit circle onto the vertical axis of the Euclidean plane. We have the same with the new functions. The Cartesian form is equal to the polar form. We normalise both sides. This brings us to the unit circle. I mean unit circle in the most general sense. We see that each of the three new functions corresponds to a projection from the unit circle onto one of the three axes of the space. This is exactly what trigonometric functions are. How about some trigonometric identities? We have the established identity. This implies the determinant of a rotation matrix is always 1. Since the determinant of an algebraic matrix form is the distance function of the space and a rotation matrix keeps invariant the distance function of the space, the determinant of a rotation matrix must be unity. We see that we have an identity with the three-dimensional trigonometric functions to match the identities of the two-dimensional trigonometric functions. We have the standard two-dimensional Euclidean addition identity. All we did was multiply two rotation matrices together. Such a product is rotation through the sum of the two angles. We have simply multiplied together two rotation matrices. The product matrix is rotation through the sum of the two three-dimensional angles. This is the three-dimensional version of the trigonometric addition identity. You are still not convinced that the new functions are trigonometric functions. Your dubiousness is natural. It will take a while before you come to accept this, but I am confident that in due time you will accept that the new functions are trigonometric functions. Why does all this work out so smoothly? It is because we are within a finite group. Ultimately, all we are doing is just combining permutations together. This three-dimensional space has its own type of three-dimensional rotation. Thus, it has its own type of three-dimensional rotational symmetries. Each space has its own type of rotational symmetries. Each space also has its own type of reflective symmetries. Within each space, there is a concept of oddness and evenness that we find within the sine and the cosine, or the cosh and the sine functions. Let us look at the oddness and evenness of the three-dimensional space. Within a two-dimensional space, such as Euclidean space, if we rotate through angle theta and then rotate through angle minus theta, we get back to where we started. This could not happen if it were not that the cosine function is an even function and the sine function is an odd function. Just try reversing the sign of the sine function in the rotation matrices and you'll see what I mean. In order for it to work, that when we rotate through a certain angle and rotate back, we get back to where we started, we need oddness and evenness. Does that work within the three-dimensional space we are looking at? Here we have a two-dimensional graph of this three-dimensional nu A function. We ought really to use three-dimensional graphs, but the point I'm trying to make is much clearer using this two-dimensional graph, and we lose nothing by using a two-dimensional graph. The left-hand side of this graph oscillates in a sinusoidal way, but with increasing amplitude as we move leftward. That is, rotate anti-clockwise. The right-hand side of this graph zooms off to infinity, a little like the cosh function, as we rotate clockwise. This does not look like an even function to our two-dimensional eyes, but in the three-dimensional sense, this is an even function. This must be a three-dimensionally even function because any rotation in the clockwise direction, that is along the horizontal axis to the right, is matched by an equivalent rotation in the anti-clockwise direction, that is along the horizontal axis to the left. Here, you are looking at a three-dimensional reflection. Here, we have the same graph at a different scale. Notice that the value of this function is unity when the angle is 0. The leading trigonometric function of any space is unity when the angle is 0. All the non-leading trigonometric functions of the space are 0 when the angle is 0. This is the same as both sets of the two-dimensional trigonometric functions. Here, you are still looking at a three-dimensional reflection. It is not unreasonable to take the view that in any dimensional space, the leading trigonometric function is an even function in terms of n-dimensional evenness, and that the other functions are odd functions in terms of n-dimensional oddness and evenness. But that's really not quite understanding things properly. In two-dimensional space, we have two trigonometric functions, and we have oddness and evenness. Because there are only two trigonometric functions, we can assign evenness to one function and oddness to the other. In three-dimensional space, we do not have this. The oddness and evenness of a space is in the rotation matrix as a whole, not in the individual trigonometric functions. Contrary to our custom view of trigonometric functions exist only within a rotation matrix. They do not exist as separate functions. This becomes particularly apparent when we deal with non-commutative spaces like the quaternion. The quaternion rotation is non-commutative, but the non-commutivity is not in the individual quaternion trigonometric functions. The non-commutivity is in the matrix. The properties of the trigonometric functions are within the rotation matrix, not the individual functions. Technically, a trigonometric function does not exist outside of a rotation matrix. Each type of space has its own type of rotation, and with that its own type of rotational symmetries. Each type of space has its own type of reflection, and with that its own type of reflectional symmetries. Within the A3 spaces, which we will meet later, the reflectional symmetry is what we call parity. We are familiar with it. Within quaternion space, there are two reflective symmetries. One is what we call charge conjugation, and the other is what we call CP invariance. Different spaces have different symmetries. We have been concerned with rotation in this three-dimensional space. But what about the distance function? Of course, the distance function of this space, the distance function that is held invariant by the rotation that we have been looking at, is the determinant of the algebraic matrix form. This is the distance function of this three-dimensional space. Notice that it is a cubic equation. In general, the distance function of a space is an equation of order equal to the size of the algebraic matrix form. The three-dimensional space that we have just looked at is beyond our observational experience. We will never see this space in our four-dimensional space-time universe. Why not? We know the answer to that, but it is not easy to explain at this time. We will get the explanation for that later in this series of videos. Well, it's been a little shocking for you. It was for me. But if you go through the mathematics, you find yourself compelled to accept the existence of this three-dimensional space and of this three-dimensional rotation, and that the new functions are genuine trigonometric functions. They are three-dimensional trigonometric functions. By the way, the reason that we call the three-dimensional trigonometric functions new functions is because we discovered them only recently. They are not very old. We have now come to the end of this second video upon the nature of empty space. Please allow me to advertise some of the books I have written. Thank you for your attention.